Now if we use this estimate of resistance, and if we manage to have 4 volts across the circuit, then how much current could we expect? Now the circuit is going to consist of the aluminum strips on the side, and what we had in class was an aluminum bar between the 2 strips. Now what you actually get in your kit consists of a piece of aluminum wire between here and here. The length and the cross-sectional area of the wire or the bar are such that there's very little resistance in it. The aluminum bar is a thin piece, actually a strip of aluminum, but it still had an area probably 100 times the area of one of the strips, maybe 1,000 times the area, the cross-sectional area, and maybe a little less length also, which means that you had a lot less resistance. For the aluminum wire that you have in the lab kit, the cross-sectional area of that aluminum wire is much less than the cross-sectional area of the strips. And in addition, the wire is a whole lot shorter than the strips, so it doesn't add much resistance. So if we could manage a 4-volt potential difference across here, how much current would we have? Well, we'd have 0.11 ohms in this strip, practically no ohms in the wire or aluminum bar, and another 0.011 ohms here, which is a total of 0.0022 ohms of resistance, which we divide into the 4-volt potential difference to give us 180 coulombs per second, or 180 amps of current. Now let me caution you that we really don't get that with the generator. If you crank the generator, the wire coils inside the generator have a high enough resistance that it's much, much higher than the 0.022 ohms here. Matter of fact, I've variously attempted to measure those resistances, and they tend to run around 20 or 30 ohms for the internal resistance of the generator. So you don't get much voltage across here is what it amounts to. Most of the 4 volts that you might well produce with the generator is lost in the generator, and very little of it goes across this circuit. Okay, most of it is used to push the current through the coils. Now, this 180 amps, which we have a question mark and an exclamation point next to because it really doesn't happen, but if we did have 180 amps through your 4-volt potential difference, which we would if we actually could get a 4-volt potential difference here, that'd probably be inconvenient. 180 amps would probably burn this aluminum almost instantly. It would just simply disintegrate. But if we did have that 180 amps, we'd have 180 coulombs per second through 4 joules per coulomb. Now from the introductory problem set, you know what all this means. 180 coulombs per second through a 4 volt or 4 joule per coulomb potential difference would imply a 720 joule per second energy expenditure, or 720 watts. We're not going to get 720 watts by cranking that generator. Our arms can't produce 720 watts even on a short burst. Our legs can. We can with our backs, but we really can't do it with our arms. At least most of us can't. There are probably some individuals, certainly a gorilla could do it, and there are probably a few human beings who might be able to do that for a very short time, but the arm would very quickly grow tired and be unable to produce any more power. In any case, we know that we weren't producing 720 watts, so we know that there weren't 180 amps through this circuit. We also know that because the aluminum didn't glow and disintegrate rapidly. Let's nevertheless pretend that we did have 180 amps somehow through this aluminum bar. Now, it would be conceivable to get 180 amps through that aluminum bar. It's thick enough, and if we had a proper source of potential difference, we could actually accomplish that. Okay? Now, if we note that this bar, which has a mass of 2.2 grams, is deflected 7/10 of a centimeter due to the 180 amp current, then we can first of all deduce the force required to deflect the thing 0.7 centimeters. The 2.2 grams can be, we can determine the weight of that 2.2 grams, and that weight will be, well, the force that deflects the 2.2 grams will be in the same proportion to its weight as the deflection to this 23 centimeters that this thing is hanging. Okay, it's effectively hanging as a pendulum. If it hangs at 23 centimeters, then we can easily determine the force. In any case, we determine the force is about 6/10,000ths of a Newton. Now we have the relationship between the force deflecting the current element and the current, the length of the element, and the magnetic field. Okay? For the magnets that we used, we estimated that the current interacts with the magnetic field over a distance of about 1 centimeter, ballpark 1 centimeter. So that's not the total length of the aluminum strip, but that's the length over which the magnetic field is felt, and that's the length that we want. Okay, so we take the current times that length over which it interacts with the magnetic field times the strength of the magnetic field should give us the force. Now, we know the current, or at least we're pretending we know that the current is 180 amps. That really isn't the current. The length of about 1 centimeter, a force of about 6/10,000ths of a Newton. What does that tell us the magnetic field is? Well, we simply take the force, the 6 times 10 to the negative 4th newtons, divide that by the current times the length to solve this equation for B, in other words. The current's 180 amps, the length is 0.01 meters. That magnetic field will then come out to be about 3 times 10 to the negative 4th newtons per amp meter. Okay, the units, of course, force is in newtons, this is in amps, this is in meters, so we got newtons per amp meter. And a newton per amp meter is the standard measured magnetic field, which is the capital T Tesla. I've crossed out the 0.03 there. Must have been looking at the 0.01, but it's a 0.0003 Tesla. So we have a 0.0003 Tesla field required to give us this deflection in this case. Now, really, the current is a whole lot less than 180 amps. And if we make an estimate that the current is 10 or maybe even 100 times less than that, maybe even more, then this field actually was a lot greater than 0.003 Tesla. Again, assuming a deflection of 0.7 centimeters, and assuming that this calculation is correct, we find that the field might have been in the order of even up to 1/10 of a Tesla. So that's actually a pretty strong field.